Hello and welcome to the third part of Lesson 5. In this part of Lesson 5, we're going to discuss the nuts and bolts of how we can fit experimental data to constitutive equations. At first sight, this sounds like a fairly straightforward exercise, but as we'll see, there's some subtleties that can catch us out. So, let's start by reviewing the equations that we'll be fitting and examining some experimental data for a real material. We're going to stick with the Phan-Thien Tanner equation. We've spent two parts of this lesson now talking about Phan-Thien Tanner, both in terms of an introductory standpoint and also operating on it to work out what the expressions for steady flow shear viscosity would be. And let's start by reminding ourselves of what those expressions are. So there on the whiteboard in green with various highlights, I've put the constitutive equation, the full convected constitutive equation for Phan-Thien Tanner, and below it I've listed the key results for the apparent viscosity as a function of shear rate and for the first and second normal stress coefficients, again found from steady shear experiments. So what we're going to do is to find some experimental data now for a polymer, a low density polythene, and that experimental data will consist of apparent viscosity data and normal stress data. So we're going to be dealing with normal stress differences rather than normal stress coefficients, and so when we're dealing with these data we of course need to convert the normal stresses into the normal stress differences and thence into the normal stress coefficient. So we've got these equations. We're going to plot some data out, we're going to have a look at some data, and then we're going to try and fit the data. Let's look at the equations to start with to see if there's anything we can glean from them in terms of limits, because this might help us specify some initial guesses for certain parameters, or may even give us great insight into what the likely value of a certain parameter is likely to be at vanishingly small shear rate. So let's examine the viscosity equation to start with. Let's look at the limit of vanishingly small shear rate. Let's say that gamma dot tends to 0. And when we look at gamma dot tends to 0, what we will see is that eta will approach eta 0. That's rather handy. And so this is sort of what we expect when we look at the experimental data. At very, very, very low shear rates, we will see, hopefully, the low shear rate Newtonian plateau, and that gives us a pretty good value for what eta 0 should be. And so we don't actually need to fit eta 0 because we can look at the data and extract a value that's pretty reasonable. Okay, let's think about the same thing in terms of the normal stress coefficient. We're going to look at the first normal stress coefficient because data for first normal stress difference is far easier to obtain experimentally than it is for the second normal stress difference. And so if we look at the equation for psi1, again as gamma dot tends to 0, psi1 tends to 2 times eta 0 times lambda. And so again, careful consideration of our experimental data could give us an initial value for lambda, because we already know eta 0 from looking at the steady shear data. And so these will give us estimates of initial conditions of the parameters that govern the problem. And as we'll see in a minute, accurate initial conditions can be rather helpful in terms of solving a problem correctly and quickly. So let's have a look at some experimental data. These data are for a low density polyethylene, it's NP-N53, at a moderate temperature of 170 degrees C, and I've extracted these data from Baird and Collias's book. So shear viscosity is in red, first normal stress difference is in blue, and remember this is the first normal stress difference, not the first normal stress coefficient. Let's look at the shear viscosity first. We can see at low shear rate the value of the shear viscosity is sort of starting to plateau. And so if we look at the lowest shear rate, 0.01 reciprocal second, we can make an estimate that our zero shear rate viscosity is going to be around 23,000 Pascal seconds, or thereabouts. It's not going to be a great deal more than that, it's not going to be a great deal less than that. And so that gives us a fairly solid estimate of what that parameter should be. Okay, let's look at the first normal stress difference now. At low shear rate, the lowest data point we've got corresponds to about 650 Pascal, give or take. We can convert that into the first normal stress coefficient by dividing by gamma dot squared. And then we can make use of the fact that for PTT at low shear rate, the first normal stress coefficient sort of goes as 2 times eta naught times lambda, which gives us an estimate of lambda of around 7 seconds, give or take. It's not microseconds, it's not hours, it's about 7 seconds. So those two parameter estimates we'll find to be quite useful in a minute, but I emphasize it's important to actually look at and understand the data before you start fitting things to the data. So let's start to set up an optimization problem now. Now what we want to do is to get the experimental data. We want to somehow process that, and we want to be able to make some predictions and then look at the difference between the predictions and what we've measured, and then change some parameters such that that difference between the measured data and the calculated data are as low as possible. So let's look into this in a little more detail. So I'm going to set up a spreadsheet. I could do this in Excel, for example, or any of the OpenOffice spreadsheets that you can find as well. And I'm going to start simply by saying, look, let's tabulate the experimental data. And I've done this simply just for 3 data points here. And of course, you can extend this out to as many as you have in reality. So I've listed the shear rates, 0.01, 0.0215, 0.0464 reciprocal second. And correspondingly, I've listed alongside that the experimentally measured values of my apparent viscosity eta. And so it goes from around 23,100 Pascal second, which was my zero shear rate viscosity, and starts to drop a little bit as I increase my shear rate a little bit. Fine, okay, those are my data. Now, in an ideal world, what I would like to do is to get the parameters that govern the prediction for apparent viscosity from PTT and calculate exactly the same values as those that I've measured experimentally. So I'm going to set up another column. In that column, I'm going to have my calculated value of apparent viscosity based on the 3 parameters that appear in the PTT model. So I've got eta 0, I've got C, and I've got lambda. And remember, for steady shear, epsilon doesn't feature. Now, what I'm going to do is I'm going to set cells with each of those 3 parameters in. So I've got eta 0, I've got C, I've got lambda. And I'm going to put as formulae in my column for apparent viscosity the formula that contains those parameters that gives me the apparent viscosity. Then what I want to do is to evaluate the difference between what I've calculated and what I've measured. And we need to do this slightly carefully, because what we're aiming for here is a single number that is greater than or equal to 0, because if it's greater than or equal to 0, what we find is if we're trying to minimize that number, the closer to 0 we are, the closer the calculated result is to the experimental result. If I haven't constrained it to be greater than or equal to 0, then of course I can minimize that into the negative domain. And that doesn't mean that my calculated result and my experimental result are close to each other if that error is strongly negative. But the optimizer will try and find the most negative value because it's trying to find the smallest value. So I'm going to constrain my error to be greater than or equal to 0. And I could simply say it's the absolute value of the difference between the calculated value of the viscosity and the experimental value of the viscosity. But I'm not going to do that, because when we're dealing with rheological data, we have to remember that that data can span orders of magnitude of difference. And so if all we do is look at the absolute difference between, let's say, that calculated viscosity and that experimentally measured viscosity, what we can sometimes find is that over the range of data that we've got, a difference that's really important at high shear rate, where my viscosity values are low, maybe order of 100, can be dwarfed by an error at low shear rate, where the viscosity values are of order tens of thousands. So what I'm going to do is I'm going to take the absolute value of the natural log of the experimental data less the natural log of the calculated data. And in that way, the natural log of these values is always going to be around order 1. It's not going to be tens of thousands. It's not going to be minus tens of thousands. And so what I can achieve by doing that is make sure that I'm trying to weight the importance of all the data points equally. That is to say that the calculated values of apparent viscosity at high shear rate affect the error by the same amount as calculated values of apparent viscosity at low shear rate. So I'm always going to take logarithmic values of the viscosities, and I'm going to frame my error around the absolute difference of those logarithmic values. Okay, so we can do exactly the same thing with my normal stress data. I'm going to list out my shear rates, I'm going to list out my experimental values of N1, I'm then going to calculate values of N1, and I can do that because PTT gives me an expression for N1. Well, it gave me an expression for psi1 that I can then convert into N1. And then I'm going to work out the difference between the experimentally measured values of N1 and the calculated values of N1 in exactly the same way that I did for the shear viscosity. Then what I'm going to do is I'm simply going to sum up all those errors and have one number that represents a global error. And that is a value that I'm going to try and minimize by changing the parameters of the PTT equation, eta 0, c, and lambda. And if I can get that sum of errors effectively equal to 0, that means that every single data point that I've calculated is very close to the experimentally measured value. Of course, it never works out that neatly in reality, but the lowest we can get that sum of errors, it's going to represent the best data fit we can obtain. Okay, so all we have to do now is change the PTT parameters to get a low error. All we have to do. So this involves choosing an optimization algorithm. And these optimization algorithms can operate in a number of completely different ways. What they're trying to do is trying to find the minimum value of a function by varying some parameters. Those parameters are linked to that function by means of a set of equations. And if we plot out as a function of each of those parameters what the values of the equation look like, we'll actually get a landscape. We'll get a contour plot. And so one way in which we can understand how different optimization algorithms work is by thinking about geological landscapes. And so here on the board I've put a picture of one of my favourite ones in the UK. This is Snowdonia in North Wales on a very unusually cloudless day. It's about one day a year that happens. And what we're going to see is how we can find the lowest value in this particular landscape. Now, this particular landscape has got a whacking great lake at the bottom of it. That lake is the lowest point. So imagine what we want to do is to find the altitude of that lake from a point higher up the cliffs around that lake. For example, if I put a ball up at the top of the copper mines there and I roll that ball downhill, that ball will find the lake. It's found the lowest point in this landscape. So what we want to ask is, how's it achieved that? What can we learn from that? And how can we apply that to a minimization algorithm? Well, what I'm going to do is to put a contour plot of the landscape on the whiteboard now. So this landscape is heavily contoured. It's very steep terrain. There's my lake at the bottom, and we can see all the contour lines, lines of constant height, surrounding that lake. Originally, I'm putting my ball up at the little lake there on the left-hand side, and it rolls downhill. And it does so by the steepest route, because that is going to be the most efficient way for it to get there. And so one of the algorithms that we find in optimization are called steepest descent algorithms, because they work out the landscape that is defined by the set of equations, the parameters of which we're trying to minimize, and then it tries to find the steepest path along those contours to get to a minimum value defined by the parameters. So the problem with steepest descent methods lies in the initial conditions. And this is sort of what I was alluding at the start of this part of this lesson. Let's zoom out on this landscape in North Wales now. So the original lake there is slap in the middle, and this was the original path my ball took, because that's where I started it. But if I changed the original geometric location of where I put the ball, we could end up in a completely different point. And so if I'd put it further along any of these ridges, I'd have found different lakes. Or I might have rolled off the end of my landscape as it tried to find sea level. And so just by changing the initial location, the initial values of the problem, I end up with completely different minimization results because it finds a different local minimum from each location. It has no way to hop over a cliff to find a minimum that is lower. It gets a bit worse than that because I could have one initial condition, say on a peak, and many different ways that a steepest descent algorithm could go from that peak if I perturb that initial condition slightly. And so, again, by means of a geological example, I could be at the peak at Gunneth again, and I could push my ball slightly to the left, slightly to the right, or slightly up and down, and it'll end up in completely different valleys. So the key point I wanted to get across here was if we're using steepest descent algorithms, your initial condition choice matters because it will influence the result. Now, there's other types of minimization algorithm. Another very basic type is called a stochastic algorithm. It's a random choice. They're also called Monte Carlo algorithms because after the game of chance in Monte Carlo. So what we do in this case is we say, I think my minimum lies in this particular area. And so we're constraining our landscape. And so what we do with our equations is we put some upper and lower bounds on what we allow the parameters to take. Much as I've got upper and lower bounds on the northings and eastings here that I can place my original ball. And then the most simple Monte Carlo algorithm randomly samples the landscape within those bounds. And it records the lowest value that it comes across. Now, of course, there's no reason to say that our definition of our constraints there has actually incorporated the lowest point we want to find, the global minimum. So we need to be rather careful how we define that search area. Now, in reality, of course, there's combinations of both of these methods. You could imagine for example, a stochastic method that does this sampling and then has a steepest descent that then carries on to find out from this particular location where do we end up. And it can then look at the various minima that it comes across and record the lowest of those minima. And so you'd be able to systematically find the global minimum to the optimization problem. Okay, so that's a very brief overview of the types of algorithms that you can get in terms of raw principles. In terms of application, if you're using something like Microsoft's Excel, the GRG nonlinear algorithm is based on steepest descent. It's a generalized reduced gradient method. The clue there is in the name. It's all about gradient. It's about steepest descent. So it's excellent and quick for very well-defined mathematical landscapes. However, constitutive equation fitting generally results in a fairly ill-defined or complex landscape. The evolutionary solver within Excel is based on a stochastic method. It will have elements of steepest descent as well. Once it's chosen a location, it will try and find what the common minima are. It might take time to get to an answer because it's doing a lot of different samples to try and get to that global minimum. And you might not actually find the global minimum because of how you defined your search area in the first place. So it's an excellent algorithm for complex landscapes. It's an excellent algorithm to find the global minimum so long as you've defined a realistic set of constraints within which it's searching. All right, let's go back to our polymeric problem. Let's go back to PTT and fitting data from rheology experiments. And I'm going to put a result here on the whiteboard for you. The original experimental data are the data points. The optimal fit are the dashed lines. And I obtained that fit by following the procedure that I've just outlined using Microsoft Excel. I've used the evolutionary solver. I specified my initial value of eta 0 because I can read it off the graph. I then made some estimates of the other parameters, lambda and Cassi, and then set the constraints such that lambda was going to be within 4 orders of magnitude and Cassi within about 4 orders of magnitude. Hopefully that gives a big enough search area, but one that can be searched within a reasonable enough time to get an answer. And within about a minute or so, we can find that the answer that C is about 0.296 and lambda is about 2.73, and those combination of parameters along with e to 0 of 23,100 Pascal second gives us the data fit that we see there on the board, which actually isn't too bad. Okay, so let's recap a few key points. Data fitting to constitutive models has to be done with care. That's the main take-home point from this part of this lesson. We illustrated this in terms of an example, which was fitting PTT's constitutive model for shear viscosity and first normal stress difference. And of course, both of these measurements are taken in shear. And we said in the last part of this lesson that it's important to incorporate extensional measurements if at all possible as well, as an engineering flow is going to have both shear and extension present in all likelihood. We also spent some time talking about optimization problems. So the key take home here is be careful. Steepest descent methods, although quick, may not give you the answer you're looking for straight away. You may need to use an evolutionary type or a stochastic type solver in order to get the global minimum of these problems.